Okay, class, good day. Let's have another topic. So for today, let's have now the acoustics in buildings. Okay, so for the definitions, of acoustics, so it is a science which deals with the production, control, transmission, reception, and effects of sound in an enclosed space. So where a sound is a human ear response to pressure fluctuation in the air caused by vibrating objects. So for example, a tap of the wall produces sounds because the tap makes a wall vibrate. So the vibrating wall produces pressure fluctuating in the air. So sound travels in space by a phenomenon called wave motion. So uh, wave motion in air is similar to the motion of a ripple produced by a dropping of pebble into a water pond. So for example, this is the water surface and you drop pebbles. Okay. So next we have the nature of sounds. So there are three types of sound. So first is speech. Next you have the music and the noise. So the physical quantities of sound is first we have the frequency. It is the number of sound ripples generated in unit of time. So the number of cycle that the air particles move back and forth in a 1 second in a sound wave is called the frequency of the wave. So its units is cycles per second. So C over S, cycles per second, which is also termed as hertz, or you have Hz. So after the Austrian physicist Heinrich Hertz from 1957 to 1857 to 1894. So that's the unit of frequency, hertz, or that is cycles per second. For the physical quantities of sounds, so there are 8 frequency bands or octaves are considered in room acoustics with the following center frequencies: 63, 125, 250, 500, 1 kilohertz, 2, 4, and 8 kilohertz. So for the low frequency, you have 63 up to 250 hertz. And then the mid frequency is 500 to 1000 hertz or 1 kilohertz. And then for the high frequency, you have 2000 to 8000 hertz. So frequency range for speech and music. So you have here the human speech. So there are vowels and consonants. So for the hearing of human range, that is only that is 20,000 hertz or 20 kilohertz. So you have the autistical laboratory test. So for human speech, for vowels and consonants, and then the music for the human hearing range, that is 20,000 kilohertz. Okay. So next we have the speed. So that is C. So the speed of sound in air has been measured as 344 meters per second. So that is the acceleration or speed. So that is equivalent to 1,130 feet per second. So this corresponds to the 1,240 kilometer per hour, or that is 770 miles per hour. So which is extremely small as compared to the speed of light, which is 300,000 kilometer per second. So the speed of sound in air does not vary with the frequency of sound or its loudness. So sounds at all audible frequency, regardless of their loudness, travel at the same speed. And then next we have the wavelength, or the symbol is gamma. So the wavelength and the frequency of sound are related to each other. As shown in the equation, speed is equal to the frequency times the wavelength. So where C is the speed in meters per time, and F is the frequency in cycles per time, and then the wavelength is in meters. Okay. So the wavelength of sound corresponds to the center frequency as shown in the table. So for the 63 hertz frequency, for the wavelength, that is 18 feet or 5.46 meters. And then for 125, that is 9 feet or that is 2.75 meters. For 250 hertz, for the wavelength, that is 4.5 feet. And then 1.338 meters. For 500 hertz, the wavelength is 2.3, and then 2.3 in feet and 0.69 in meters. For 1000, that is 1.1 feet and 0.34 in meters. For 2000 hertz, that is 0.6 in feet and 0.17 or 0.17 in meters. And then for 4000 hertz, that is 0.3 in feet and 0.09 in meters. And last, you have for 8000 hertz, that is 0.15 feet or that is 0.04 in meters. So that's the frequency corresponding with their wavelength. So next, we have the intensity. So intensity is defined as the amount of sound power falling on or passing through or crossing a unit area. Since the unit of power is watt, so the unit of sound intensity is watt per square meter. So W over meter squared. Okay, then the sound intensity, which is just audible, called the threshold of audibility, has been determined to be raised 10 raised to the power of -12 watts per meter squared. And the intensity that corresponds to the sensation of pain in the human ear is approximately 10 watts per square meters. So that's the physical quantities of sound. So first is the frequency. Next, we have the speed, and then the wavelength and the intensity. So let's have now the characteristic of sound. First, we have the loudness. So it is measured, it is a measure of intensity of sound and is expressed in decibels. So it is a quantity called the sound intensity level or IL. So you have here the sound pressure in Pascal, and then the sound intensity in watts per square meters, and then the sound intensity level or the sound pressure level in terms of decibel, and the noise in the environment. So you have here the data. So you just go through with this data. You have a copy of this slide. And then next, for the characteristic of sound is pitch. So it is the frequency of sound wave perceived by the human ear. So a high pitch sound means that it has a high frequency. So the female voice is slightly higher pitch than the male voice. So next, we have the acoustical concern in architecture. So noise control. So since mostly the design of acoustics in building will be performed by the architects. So as we engineers, maybe we can design that, but the basic knowledge only for the acoustical controls. For the architecture, they will maybe study all about the acoustics in building. But for engineers, we have just the basics. Okay, so for the noise control, so this involves the following activities. the control of airborne noise through the insulation or insulation of sound, or the shutting out of unwanted sound from the outside. So this requires a study of the sound, insulating values of walls, partition doors, and windows, and a study of ventilating system to provide a basis for the reduction of the transfer of unwanted sound from one room to another. And also the control of structure-borne noises through the isolation of machines from the room or from the building structure. Okay, and then we have the principal acoustical defects of room. So first is prolonged reverberation. So long reverberation time, or RT, due to large amount of highly reflected surface and or to large volume of spaces, which will take considerable time for reflected sound to die out. So effect of prolonged reverberation is blurring, which is harmful to both speech and music. So maybe in cinemas, so architects, maybe they can design a cinemas or theater, they will have to minimize reverberation. Reverberation time is influenced by the volume of the room. So if you have bigger room, so it can influence the reverberation time. And then the sound absorbing abilities of the room surfaces. So maybe you have a smooth surface, or maybe you have a rough surface. And then the number of people and furnitures in the rooms. Okay. Next, we have the echo. So distinct reflection of original sound, which result when the path of reflected sound is 20 meters, or that is 65 feet or more than the path of the direct sound. So if the difference is less than 20 meters, the reflected sound will reinforce the direct sound, which is desirable. So I think you know already what is an echo. So maybe you shouted and then the sound created with your mouth goes back to you. That's the echo. So it is recommended that the surface of the front part of the auditorium must be highly reflective to reinforce direct sound and through it to the rear of the room. So on the other hand, the rear must be highly absorptive, so the delayed direct sound will be absorbed and not be reflected to the front. So that is why when you shouted, maybe a front is reinforced with reflective material, and then it bounces to your rear material. So the rear material should be a sound or sound absorptive, no? Absorptive. Okay. Next, we have the resonance. So resonance is the reinforcement of certain sound frequency due to sympathetic vibration. So this is especially the case in enclosed room with highly reflective surfaces. So the effect would be emphasize certain frequencies at the expense of others. So which is undesirable for balanced desire in the rooms intended for music. And then you have a flutter echo. So flutter echo is a rapid but repetitive succession of sound caused by a highly reflective parallel surface. So wall to wall or ceiling to floor. So that is parallel. And then you have undue focusing of sound. It is caused by concave surfaces, which causes sound to converge at certain point with resulting loss of energy in other parts of the room. So maybe if you have curved surfaces or concave surfaces, you can achieve undue focusing of the sound. So now let's have the glossary or of the important acoustical terms or the definition of terms used in acoustics. So first, you have the absorption coefficient. So the fraction of the incident sound energy absorbed by a surface. Next is anechoic chamber, a sealed room in which all the surfaces are designed to completely absorb all sound produced in a room. And then attenuation. So this is a reduction of sound level. So sound attenuation in air conditioning is specified in terms of decibel per meter. Next, you have the background noise, or that is an ambient noise. So maybe in video calls, you have a background noise, maybe bark of an animals or a dog, no? A sound, or maybe a sound of or noise coming from other machines like the air conditioning unit. So that's the background noise or the ambient noise. Next, we have break-in noise. So transfer of noise from a space surrounding the duct into the duct through the duct wall. So duct, that is in mechanical use. No? You have the air conducting. So that's where it's transfer the noise. Okay. Then that's break-in noise. So break-out noise is the transfer of noise from the interior of a duct through duct walls into a space outside the duct. And then we have the dead room, a room containing an unusually large amount of sound absorption. So dead room, so you have maybe a soundproof room. That's a dead room. And then the decibel is a unit of measurement for sound pressure level, sound intensity level, or a sound power level. The next, we have the diffraction. It is a change in the direction of propagation of sound as a result of bending caused by a barrier in the path of the sound wave. And then you have diffuse sound or field. So a sound field in which the sound comes in equal intensity from all direction. Maybe a smooth surface wall. So that can achieve diffuse sound. And then direct sound. So the sound that arrives at a receiver along a direct line from the source without reflection from any surface. And then you have the echo, a sound that has been reflected with sufficient time delay. So you already know that. And then environmental noise, exterior background noise in a neighborhood. So example, the traffic, the aircraft, or maybe another sound caused by environmental or a sound caused by the environment or your surroundings. And then fidelity, faithful reproduction of a sound source. You have also a flutter echo here, a rapid but repetitive succession of sound from a sound source, usually occurring as a result of multiple reflection in a space with hard, flat, and parallel walls like wall-to-wall, and then ceiling to floors. Next, we have the frequency, the number of full cycles per second measured. So the unit is in hertz. Next, we have the impact noise, noise caused by collision of two objects. So that's impact. Then we have the infrasonic, a sound that is below the human audible frequency. So that is below 20 hertz. So insulation, or you can also, or another term for insulation is isolation. Next, we have intermittent sound, a sound which is discontinuous or fluctuates to such an extent that at times its sound pressure level falls below the measurable level. Then we have an inverse square law, a law which states that the sound intensity in a free fields varies inversely with the square of the distance from the source. So for the isolation, or that is insulation, a lack of acoustical connection. So you have also a leak, a small opening in a barriers that allows airborne sound to pass through. And then a live room, so a room containing an unusual small amount of sound absorption. So unlike the dead room, that may be a room that is fully, I think a fully isolated room. So that's a dead room. Okay. And for the live room, that is small amount of absorption. And dead room is a large amount of sound absorption. Next, we have the loudness. So for the loudness, an auditory sensation that depends on sound pressure level and the frequency of sound. So you have the loudness. So masking, the increase in the threshold of audibility of a sound that is required so that the sound can be heard in the presence of another sound. So that is masking. Then you have the noise isolation class or NIC, a single number rating derived from the measured value of noise reduction between the two rooms. And then the noise reduction or NR, so the reduction in sound pressure level or noise. You have also noise reduction coefficient, so a single number rating derived from measured values of sound absorption coefficients of material at 250, 500, and then 1000 and 2000 hertz. So that is the noise reduction coefficient. Another, we have outdoor indoor transmission class or OITC. That is a weighted single number rating on the sound reduction effectiveness of a partition that separates an indoor space from the outside. And then the pitch, a listener's perception of the frequency of a pure tone. Okay. Pitch. Another, we have reflection coefficient, a measure of the sound reflective property of a surface. And then the resonance, the relatively large amplitude of vibration produced when the frequency of the source of sound is equal to the natural frequency of a room. And then you have reverberant sound fields, a sound field created by repeated reflection of sound from the boundaries in an enclosed space. And then we have reverberation, the continuation of sound in an enclosed space after the initial sound has been terminated. So that's reverberation. And then reverberation time or RT, the time it takes the sound intensity to decay by 1 millionth or of its steady state value after the sound source has been terminated. And then you have the Saben, a unit of measure of sound absorption. And then scattering, an irregular diffraction of sound in many directions. So we have also sound insulation. So the ability of a barrier to protect, to prevent sound from reaching a receiver. And then a sound intensity, SI, the average rate of sound energy flow through a unit area in a given direction. And the sound intensity level, so quantity expressed in decibels of airborne sound. And then the sound lock, a small space that works as a buffer between a source room and a receiving room. And also we have a sound pressure, fluctuating pressure of sound superimposed on a static air pressure. And then you have sound pressure level, C, sound intensity level. So you have, and the other term for sound pressure level is sound intensity level or SIL. And then we have sound transmission class, STC. This is a single number rating of the sound insulation rating of a partition. And then you have structure-borne sound, sound propagated through a solid structure. We have also transmission coefficient. So that is the ratio of transmitted sound energy to incident sound energy. And then you have transmission loss. It is measured of sound insulation of a partition. And then we have wavelength. This is the distance between two adjacent compressions or rarefaction in a sound wave. And then last, we have the white noise. This is a noise whose energy is uniform over a wide range of frequency. This is analog to the term white light, which consists of almost equal amount of light of different wavelengths or color. So a white noise sounds hazy. So that's the end. So thank you for viewing and listening this discussion. See you in our next discussion. Thank you.